When we talk about the James Webb Space Telescope, we usually think of spectacular images, glowing nebulae, star-forming regions that look like oil paintings, galaxies stretched into delicate arcs by gravity. But hidden behind those headlines is something stranger and much quieter, a population of tiny, almost featureless specks that are starting to rewrite what we thought we knew about the early universe. Astronomers have started calling them little red dots. In JWST's deep infrared images, they don't look like spirals or chaotic blobs. They don't show delicate structure or long tidal tails. They are just compact, extremely red points of light, often no larger than a pixel or two on the detector, and yet they seem to live in an era when the universe was still very young. These little red dots don't appear in the nearby cosmos. They show up at enormous redshifts, corresponding to a time roughly between about 600 million and 1.6 billion years after the Big Bang, when the first generations of galaxies and black holes were still assembling. The red in their name isn't a color in the everyday sense. It reflects the fact that their light has been stretched by cosmic expansion into the infrared, and that their spectra are dominated by very long wavelengths. JWST, with its infrared eyes, is uniquely sensitive to that faint, stretched-out glow. On raw images they look deceptively simple, no arms, no clear clumps, just a tiny, concentrated point. But when you analyze their brightness, their colors, and their implied masses, they stop being simple at all. The central mystery is straightforward to pose and very hard to answer. What are we actually looking at? One possibility is that many of these objects are ultra-compact, rapidly growing galaxies, dense knots of stars and gas that happen to be small but incredibly active. Another, more unsettling interpretation is that a significant fraction of the light is coming not from stars, but from voracious black holes at their centers, early active galactic nuclei that are already millions or even billions of times the mass of the Sun, shining as they consume gas at furious rates. That in turn would mean that supermassive black holes were already in place astonishingly early, amplifying the existing puzzle about how such massive objects could grow so fast in such a short time after the Big Bang. And there is a third option, hovering at the edge of current theory, that some of these dots could represent a new kind of hybrid object, where the distinction between galaxy and black hole begins to blur. Ideas like black hole stars or massive envelopes of gas, heated and held together by a central black hole, have been explored in theoretical work. In that picture, the early universe might have hosted strange entities where a growing black hole and its surrounding stellar nursery coexisted as a single compact beast, lighting up the infrared sky as a single red point rather than a resolved galaxy. JWST's little red dots sit right in the parameter space where such exotic objects might live, and that is part of what makes them so provocative. So the video opens with a simple image, a deep JWST field, full of faint galaxies and delicate arcs, and scattered among them, tiny crimson pinpricks. At first glance, they look insignificant, like noise. But each of those dots could be the core of an infant galaxy, or the glare from a feeding monster, or the visible skin of something we do not yet have a proper name for. In the deep infrared light of James Webb, we are not just seeing pretty pictures. We are seeing the most compact, most enigmatic structures in the young cosmos pushed right to the edge of detectability. The framing question for the viewer is clear. Are these little red dots the first cities of stars, the first great black holes, or the fossils of some short-lived, exotic phase of cosmic evolution that we are only now discovering? By the end of the introduction, the audience should feel that tension. The data are real, the objects are there, but their nature is still open. Each pixel-sized glow carries the mass of millions or billions of suns, compressed into a volume too small to resolve. The universe is showing us tiny red punctuation marks in its early story, and inviting us to guess whether they are full stops, commas, or exclamation points. Little red dots, or LRDs, are not a single odd object or a handful of strange outliers. They are an entire new class of sources that JWST has dragged out of the early universe. In the data, they look deceptively simple, extremely compact, almost point-like blobs that glow a deep, intense red in the infrared bands where Webb is most sensitive. They are so small on the sky that, even with JWST's sharp vision, many of them are effectively unresolved. Each appears as a tiny knot of light, with no obvious spiral arms, no visible clumps, no stretched tidal features. What makes them intriguing is not just their shape, but when and where they live. Their colors and spectra place them at very high redshifts, roughly in the range Z-4.5 to 10, which means we are seeing them as they existed when the universe was between about 600 million and 1.6 billion years old. In other words, these are not quiet, macho systems in a settled cosmos. They are compact powerhouses sitting squarely in the era when galaxies and black holes were first assembling. Their defining properties come in a tight bundle. First, they are extraordinarily compact. Their apparent sizes are at or below JWST's resolution limit, so that even careful modeling of their light profiles often yields half-light radii of just a few hundred parsecs or less. Second, they are very red in the infrared, which can signal several things at once: strong redshift, heavy dust obscuration, or a very old stellar population, even though, cosmologically, very old at that epoch still means only a few 100 million years. Their spectral energy distributions often show steep rises toward longer wavelengths, hinting at large masses packed into tiny volumes. Third, they are intrinsically rare and faint. They sit at the edge of what JWST can currently detect, demanding ultra-deep exposures and careful analysis to separate them from noise and from more ordinary galaxies. Despite those challenges, surveys using JWST's deepest fields have already catalogued hundreds of these objects, of order 300 or more candidates that share this same combination of extreme compactness, redness, and high redshift. That number matters. It tells us we are not dealing with one freak galaxy here, one unusual quasar there, but with a population. LRDs appear again and again in different JWST fields, in different observing programs and analyses, emerging as a new statistical component of the early universe. They live right at the observational frontier, where every photon is precious and every measurement carries large uncertainties, but taken together they point to something systematic happening in that young cosmic era. In this segment of the video, the viewer should come away with a clear baseline picture. Little red dots are tiny, intensely red, very distant compact sources, first formally recognized and described as a distinct class in 2024, now known in the hundreds, and they represent a new family of objects that we simply did not see, or could not see, before JWST flew. They are, in essence, the punctuation marks of the early cosmos, dense, bright dots embedded in the faint fog of newborn galaxies and ionizing radiation. The rest of the video will be devoted to asking what is hiding inside those dots. But first, we need to sit with the fact that they are real, numerous, and so extreme that they push even our best telescope to its limits. JWST saw the little red dots by doing something Hubble physically could not. It reached into a much redder, fainter part of the spectrum where the earliest galaxies and black holes now hide. Over billions of years, as the universe expands, light from distant objects is stretched to longer wavelengths. What might have started as bright ultraviolet or visible emission in the first few 100 million years after the Big Bang arrives at us today as deep infrared. Hubble was a masterpiece for its time, but it was designed mainly for visible and near-infrared light. Its sensitivity drops exactly where the most distant, highly redshifted objects now live. For extremely compact sources that are both faint and very red, Hubble effectively looked into the darkness and saw almost nothing. JWST, by contrast, was built precisely to see the ancient, stretched light from the early universe. Its NIRCam instrument is tuned to a suite of infrared filters that reach far beyond Hubble's range, and with a far larger mirror it can gather many more photons from each tiny patch of sky. When astronomers pointed JWST at deep fields and star-forming regions, something new appeared in those redder filters, tiny, unresolved pinpoints that lit up strongly only at long wavelengths, barely or not at all visible in the blur bands. That combination, strong infrared brightness, extreme redness, and almost point-like size, became the selection fingerprint of the little red dots. The identification process works like a kind of cosmic color-based detective work. Astronomers first look for sources that become dramatically brighter in the reddest NIRCam filters compared to the bluer ones, a sign that much of their light has been shifted out of the optical range by cosmic expansion or heavily reprocessed by dust. Then they examine how compact these objects appear in JWST's exquisitely sharp infrared images. Many of the LRDs collapse down to almost pure point sources, with sizes that push against the limits of what the telescope can resolve at those distances. That rules out large, diffuse galaxies and points instead to either extremely compact stellar systems or intense activity around central black holes. When these criteria were applied systematically to the deepest JWST fields, the result was startling, not one or two, but an entire forest of such red, compact dots scattered across the early universe. Hubble, with its more limited infrared reach and lower sensitivity at those wavelengths, simply did not have the eyes to see them. For it, These objects were either invisible or blended into the noise. JWST turned the infrared darkness into a landscape and, in doing so, revealed that the young cosmos is sprinkled with these enigmatic little red beacons. From that moment, it was clear that astronomers were not just filling in details of a known picture, they were confronting a genuinely new population that demands an explanation. When astronomers started to fit spectral energy distributions for the little red dots, they quickly realized these were not just ordinary tiny galaxies hiding in the noise. By combining JWST's multifilter photometry, they can reconstruct how bright each object is at different wavelengths and compare that pattern of light with physical models. From the shape of the SED and the relative brightness in each NIRCam filter, they estimate a photometric redshift. For many LRDs, this falls roughly between Z-4.5 and 10, meaning we are seeing them when the universe was only a few hundred million to about 1.5 billion years old. At those redshifts, even a small apparent brightness can correspond to a huge intrinsic luminosity, because the objects are so far away. When they then feed these luminosities into stellar population models, what kind of mix of stars and ages would produce this light? They often get surprisingly large stellar masses, in some cases up to billions of solar masses packed into something that appears almost point-like. That alone would be remarkable. Such compact, massive systems emerging so early challenge our expectations for how fast galaxies can assemble. But the puzzle deepens when you look at the ratio between total stellar mass and observed luminosity. For many little red dots, the light is too intense, too concentrated, and too red to be explained comfortably by stars alone, especially if those stars are already somewhat evolved. If you model them as purely star-forming galaxies, you either end up with extremely extreme bursts of star formation happening in very small regions, or with stellar populations that don't quite fit the observed colors and brightness. This is where dust and black holes enter the story. Some of the redness could be due to heavy extinction, dust grains absorbing blue and ultraviolet light and re-emitting in the infrared, wrapping the entire system in a warm, murky glow. But even dust-reddened starlight struggles to explain the compactness and luminosity of many LRDs. A natural alternative is that a significant fraction of the radiation is coming from accretion onto a central black hole, an active galactic nucleus so deeply buried in gas and dust that we never see the sharp quasar-like features we're used to, only a red, compact, infrared bright dot. In that picture, the SED we fit is a blend, some starlight from a tiny, extremely dense host, plus a powerful, dust-reprocessed glow from a rapidly growing black hole. The first measurements don't give us a single clear answer. Instead, they reveal a tension. Either galaxies were assembling mass, metals, and dust much faster than our standard models predict, or we are looking at a population of nascent quasars whose black holes are already punching far above their expected weight this early in cosmic history. The little red dots, through their masses, brightness, and redshifts, are effectively telling us that something about our understanding of early galaxy and black hole growth is incomplete. In the first and currently most popular scenario, the little red dots are not exotic new kinds of objects, but a very extreme version of something we already know, tiny, hypercompact galaxies whose light is dominated by an active supermassive black hole at the center. In this picture, each LRD is like a newborn galactic core, a dense swarm of young stars and gas wrapped tightly around a black hole that is feeding as fast as physics allows. Instead of the graceful spiral disks and extended halos we are used to seeing in nearby galaxies, here almost all the visible action is compressed into a region so small that, even for JWST, it looks like a single red pixel. The reason these dots are so bright and so red is that much of their energy is coming from matter spiraling into the central black hole. As gas falls inward, it heats up, produces intense radiation, and then gets absorbed and re-emitted by surrounding dust. That reprocessed energy emerges mostly in the infrared, exactly where JWST is most sensitive, turning the whole system into a miniature furnace glowing in deep red. When astronomers model the light of LRDs under this assumption, they find that a large fraction of them show clear signatures of active galactic nuclei. Their colors, luminosities, and compactness line up far better with an accreting black hole plus a small host than with a purely stellar population. Even more striking, in many of these systems the inferred black hole mass appears oversized compared to the amount of stars in the surrounding galaxy. In our local universe, the mass of a central black hole is usually just a tiny fraction of the stellar mass of the galactic bulge, like a pinprick in the middle of a city. But in the little red dots, the black hole might already represent several percent of the host stellar mass, sometimes even more, as if the city center grew faster than the city itself. That suggests that, at least in the early cosmos, black holes may have outpaced their galaxies, swelling quickly while the rest of the structure was still assembling around them. If this interpretation is right, LRDs are snapshots of a crucial moment in cosmic history, young galaxies in which the central engine has turned on very early, blasting out energy that will eventually regulate how many stars can form and how the galaxy will evolve. The balance is delicate, too much feedback, and the system will blow away its gas and stunt its own growth. Too little, and it will collapse under its own overproduction of stars. The little red dots seem to occupy this dangerous, fascinating middle ground, compact protogalaxies whose black holes are already punching far above their weight, turning them into cosmic lighthouses that shine disproportionately bright compared to their small size. In a poetic sense, these objects might be the first downtowns of the universe, tiny, overcrowded city cores where the central black hole has begun devouring its surroundings faster than the rest of the city can expand, leaving us with a scene where the monster at the heart of the galaxy has grown almost as fast as the galaxy itself. In the second scenario, the little red dots are not dominated by ravenous black holes at all, but by extreme, dust-choked bursts of star formation compressed into spaces barely larger than a galactic nucleus. In this interpretation, an LRD is a hypercompact stellar clump in the early universe, a tiny galaxy, or the dense core of a forming galaxy, where stars are being born at such an intense rate that their combined light must fight its way out through a thick, turbulent shroud of gas and dust. That dust absorbs the harsh ultraviolet and visible radiation from newborn massive stars and re-emits it in the infrared, making the entire object appear very red in JWST's filters. The result is a system with astonishing surface brightness, a huge amount of stellar light packed into an incredibly small apparent size, like a cosmic city whose entire population is crammed into a single glowing block. From a distance, through JWST's eyes, it looks like a single red pinprick, but physically it could be a swarm of clusters, supernovae, and violent winds all trapped together inside a dusty cocoon. The difficulty with this picture is that, if the light truly comes only from stars, then many of these systems must already host stellar masses that rival or even exceed those of mature galaxies like the Milky Way, and they must have assembled that mass within just 500 to 700 million years after the Big Bang. That strains standard models of galaxy formation, which generally build such large systems more gradually. Yet the data are not clean enough to exclude pure starburst explanations for all LRDs. In some cases, the spectra and colors can be fit without invoking an active black hole, especially if one allows for very high dust content and unusual star formation histories. For now, the dusty ultra-compact starburst scenario remains a serious competitor, a vision in which at least part of the little red dot population consists of young galaxies caught in an almost unimaginably intense, short-lived phase of stellar birth, their true size and structure hidden behind a veil of cosmic smoke. Astronomers now suspect that some of JWST's little red dots might be far stranger than compact galaxies or dusty starbursts. One of the most exotic ideas on the table is that a fraction of these objects could be black hole stars, quasi-stars powered not by fusion in their cores, but by a central black hole wrapped in an enormous envelope of gas. In this scenario, a massive gas cloud collapses in the early universe, but instead of forming an ordinary star, its center implodes directly into a black hole. That black hole does not stay naked. It becomes cocooned inside a vast, opaque atmosphere. As matter falls inward, it releases enormous amounts of energy, heating the surrounding gas and making the whole object shine like a monstrous, swollen star. From a distance, such an object would look like a tiny, incredibly bright, very red point, compact enough to be unresolved even for JWST, but far too luminous for its apparent size if it were made only of normal stars. For some of the little red dots, their spectra and brightness profiles fit uncomfortably poorly into the usual categories of small galaxy or ordinary active nucleus. They seem too compact for standard galaxies, and their light is concentrated in a way that hints at extreme central power sources rather than a spread-out population of stars. One particularly intriguing candidate has earned the nickname the Cliff because its spectrum shows an abrupt, cliff-like jump in brightness between two wavelengths, a sharp edge that is difficult to reproduce with normal stellar populations alone. Models that include a central black hole embedded in a dense, inflating envelope of gas can naturally create such steep features, because the radiation escaping from the envelope is shaped both by the accretion physics near the black hole and by the thick layers of material around it. In that picture, The star is really an atmosphere wrapped around a feeding gravitational monster, glowing as infalling gas is converted into light. The idea of black hole stars is still firmly in the realm of theory and early modeling. No one can yet point to a single object and declare with certainty, this is a black hole star. The data are noisy, the distance is enormous, and the degeneracies between different models real. Compact dusty galaxies, extreme starbursts, and small galaxies with rapidly growing central black holes can mimic many of the same signatures. But the very existence of these puzzling little red points forces astronomers to consider such exotic scenarios. If even a few of them turn out to be quasi-stars, brief, furious phases in which a nascent black hole is wrapped in a stellar-sized shroud, they would offer a missing link between the first collapsing gas clouds and the gargantuan black holes we see anchoring galaxies today. In that sense, the little red dots might not just be galaxies in miniature, but snapshots of a transitional, violent stage in cosmic evolution, when gravity, radiation, and gas briefly balanced in an almost impossible configuration before collapsing into the more familiar structures we see in the local universe. Kuiper's LRDZ9 is one of the clearest examples of how extreme these little red dots really are. Imagine looking back to a time when the universe was only about 500 million years old, less than 4% of its current age, and finding a compact red speck whose light carries the fingerprints of a rapidly growing black hole. That is what this object represents, a tiny, unresolved source at redshift Z-9 whose spectrum and luminosity imply the presence of a central black hole with a mass on the order of 10 suns, buried inside a very young system that has only just begun to assemble its stars. In the local universe, supermassive black holes typically make up a small fraction of a galaxy's stellar mass, but in Kuiper's LRDZ9 the balance appears heavily tilted. The black hole is overgrown compared to the surrounding stellar population, more like a nucleus that has raced ahead of the galaxy that hosts it. For galaxy formation models, this is deeply unsettling. To reach tens or hundreds of millions of solar masses by such an early epoch, the seed black hole must either have formed already massive, perhaps through direct collapse, or have accreted gas at extraordinarily high rates for a significant fraction of cosmic history, pushing against or even beyond the usual theoretical limits on growth. Kuiper's LRDZ9 is not an isolated curiosity, either. It belongs to a growing family of LRDs with strong signs of active galactic nuclei, broad or high ionization emission lines, extreme compactness, and luminosities that are difficult to explain with stars alone. Together, these objects suggest that the early universe went through a phase of intense, but often dust-shrouded, black hole growth, where many of the first galaxies were less cities of stars and more engines of accretion wrapped in gas and dust. In that picture, Kuiper's LRDZ9 becomes a kind of archetype, a tiny red point in JWST's deep images that, under detailed scrutiny, turns out to be a young galaxy where the central black hole has already become the dominant actor, shaping the light, the gas, and possibly the entire future of the system. Compared to the classical quasars and active galactic nuclei we know from the later universe, the little red dots look like a different species altogether. Traditional quasars are the cosmic show-offs. They blaze across the electromagnetic spectrum, often saturating X-ray and ultraviolet observations, with large host galaxies that, even if faint, can usually be resolved or at least inferred from their extended light. Little red dots, by contrast, are tiny and self-contained. In JWST images they are almost point-like, often no bigger than a single pixel, and their light is pushed deep into the infrared, giving them that characteristic compact, ruby-red appearance. When astronomers look for the usual signatures of powerful active nuclei, strong X-ray emission, broad emission lines plus a bright surrounding galaxy, they often find a more ambiguous picture. In many LRDs the X-ray signal is faint or entirely absent at current sensitivities, which is surprising if these objects host rapidly accreting black holes comparable in power to classical quasars. One obvious explanation is heavy obscuration. Thick cocoons of gas and dust could be swallowing the high-energy radiation before it escapes, letting only the reprocessed infrared glow leak out. But geometry and youth likely matter just as much. In a mature quasar, the black hole sits in a relatively established galactic environment, with a large, structured disk and a more stable torus of dust. In an LRD, we may be catching the system in its first, chaotic ignition phase, when gas is still pouring in, the surrounding galaxy is barely assembled, and the central engine is buried inside a dense, turbulent envelope. That would naturally produce a source that is extremely compact, extremely red, and dominated by a small region of intense accretion rather than by a fully grown stellar population. Another key difference is the balance between black hole and host. In classical quasars, the central black hole typically represents a tiny fraction of the galaxy's stellar mass, following well-studied scaling relations. In many little red dots, preliminary measurements suggest that the black hole may be unusually massive for the size of its host, hinting that the black hole's growth has outpaced, or even driven, the earliest stages of galaxy assembly. Put together, these clues point to LRDs as a distinct evolutionary phase, not yet the broad, blazing quasars of the later cosmos, and not just dusty starbursts, but something like embryonic galactic nuclei in which the central black hole is still carving out its environment. In that sense, the difference between a little red dot and a classical quasar is the difference between a newborn engine just sputtering to life in a shroud of smoke and a fully tuned machine roaring in open air. Both are powered by gravity and accretion, but the conditions around them, and the way they reveal themselves to us, are profoundly different. Little red dots are much more than a curiosity in JWST images. They are signposts pointing straight into the most formative, chaotic years of the universe. When we look at them carefully, they tell us that massive black holes and extremely compact galaxies were already in place far earlier, and growing far faster than the standard models of structure formation ever really expected. In the classical picture, small galaxies formed first, slowly merging and feeding their central black holes over hundreds of millions, even billions of years. But the existence of LRDs at only a few 100 million years after the Big Bang, already hosting powerful accretion, and in some cases seemingly overgrown black holes, suggests that nature had more shortcuts than we thought. These tiny crimson points compress into themselves several puzzles at once: how to assemble so much mass so quickly, how to ignite black hole growth before the host galaxy is mature, and how to cloak that process in dust and gas so that most of the light slides into the infrared. In that sense, each little red dot is like a freeze frame of a prototype quasar, caught at the moment when the black hole is starting to dominate its environment. They also act as a laboratory for testing our scenarios of early structure formation. If many LRDs do indeed originate from direct collapse of massive gas clouds, they strengthen the idea that, in the young universe, some regions skipped the ordinary star-first route and fell straight into black holes of tens or hundreds of thousands of solar masses. If instead a significant fraction are powered by more conventional seeds that simply grew amazingly fast, that pushes us toward models with bursts of super-Eddington accretion or extremely dense protogalactic environments where mergers and inflows were more violent than we have assumed. Either way, they force us to confront the detailed role of dark matter halos, gas cooling, and cosmic environment. How concentrated must a halo be to channel so much matter to its center? How does the spin of that halo affect inflow? And how does the surrounding web of filaments feed these embryonic galactic nuclei? LRDs also tighten the link between early galaxy growth and early black hole growth. The fact that so many of them appear compact, overmassive in their nuclei, and heavily obscured hints that the first supermassive black holes may have grown in a brief, hidden phase before they emerged as the bright, classical quasars we see at slightly later times. From a cosmological point of view, this reshapes the timeline. Instead of black holes gently catching up with their galaxies, we may be looking at a universe where black holes led the way, sculpting their hosts from the inside out. In that sense, little red dots are not just distant, anonymous pixels. They are scars on the young face of the cosmos, the burn marks left by the first engines powerful enough to rearrange gas, turn on and quench star formation, and light up the dark with their buried, infrared glow. The more of them we find, the clearer the message becomes. The early universe was not a quiet nursery of slow, gentle growth, but a storm of compact, intense structures where galaxies and their central monsters were born together, in a rush. When we talk about little red dots, the most honest thing we can say is that they sit right at the edge of what we understand, and just beyond it. We still don't know what fraction of these objects truly host actively growing black holes and what fraction are only extreme, compact star factories buried in dust. Photometry and early spectra strongly hint at a large AGN population, but the exact numbers depend on how we model dust, stellar populations, and accretion light, and small changes in those assumptions can move an object from black hole dominated to starburst dominated in a single fit. We also don't yet know the real masses of their black holes and stellar components with any precision. Are their central black holes genuinely overgrown for their size? Or do our current models simply underestimate how fast tiny galaxies can form and age their stars in the early universe? Deeper, higher-resolution spectra and more refined dust and stellar templates are needed before we can say where those masses truly lie. On top of that, there is the most tantalizing question of all. Are any of these objects actually something more exotic than galaxy plus black hole? A few candidates have spectral shapes and compactness that look suspiciously like the theoretical black hole stars or quasi-stars, huge, glowing gas envelopes powered by a central black hole rather than nuclear fusion. But right now they remain suggestions, not confirmed discoveries. Around all of this, there is a very active debate. Some teams see in LRDs clear evidence that massive black holes were already shaping the early cosmos far more aggressively than expected. Others argue that we are looking at the most extreme compact galaxies, where furious star formation and heavy dust mimic the signatures of an active nucleus. A third camp points out that if neither of those explanations fits all the data, we may be glimpsing new physics of gas collapse, feedback, or even gravity itself in the high redshift universe. Papers, counterpapers, and new JWST observations are appearing constantly, each shifting the balance a little, but not yet closing the case. And that is precisely what makes little red dots so compelling. They are not a solved puzzle that we are calmly explaining after the fact, but a live mystery unfolding in real time. For now, they remain tiny crimson specks on JWST images and oversized questions in the minds of cosmologists. Reminders that even with our most powerful telescope, the early universe still knows how to surprise us. When we talk about JWST's little red dots, it's easy to forget what we are actually looking at. On the image, they are just a few overexposed infrared pixels, tiny smudges on a dark background, almost lost among graceful spiral galaxies and stretched arcs of lensed light. But each of those dots could be an entire cosmic city of stars, or the blazing cocoon of a newborn supermassive black hole that started growing when the universe was still in its first few 100 million years. Little red dots are not one simple category. They are a new population that lives right at the edge of what our telescopes can see. Some of them behave like ultra-compact galaxies, packing extraordinary amounts of mass and energy into volumes so small that our standard models of galaxy growth strain to explain them. Others show signs of actively accreting black holes, where most of the light comes not from stars but from matter spiraling into a central engine, outshining the entire host galaxy wrapped around it. And perhaps, hidden among them, there are even more exotic possibilities. Envelopes of gas powered by embedded black holes, transitional objects that don't quite fit our familiar labels of galaxy, star, or AGN. What makes these dots truly important is not only what they are, but when they appear. They show up far earlier, and in greater numbers, than many of our theories would predict. They hint that massive black holes and dense stellar systems were forming more rapidly and more violently than our standard pictures of slow, hierarchical growth would suggest. They force us to revisit ideas about direct collapse of gas clouds, extreme early accretion, and the role of dark matter halos in seeding the first luminous structures. So the honest conclusion is that little red dots are not just curiosities in JWST images, they are keys. Keys to understanding how the first galactic cores assembled, how supermassive black holes gained their initial mass, and how a smooth early universe turned into one filled with complex, structured light. We look at blurred, crimson specks in the depths of the sky, but behind each of them lies an entire history of collapse, ignition, and growth. Perhaps, in these small red letters written on the black page of the early cosmos, the universe has left us a note explaining how it managed to become adult so quickly. And as JWST continues to collect ancient photons from the first hundreds of millions of years, we are only just learning how to read that message, slowly turning those little red dots into answers about our cosmic beginning.